our concatenated string to be the size of the buffer, then we're going to print it out. That's it. That's all there is to it. So countdown, very super obvious. It just says that it's counting down. It prints out the values and then says that it's done. Concatenation, we're just going to use string n copy to get the first word into the buffer, then use cat to get the second word in. We need to make sure that we limit the size, the total size of the buffer by the first word that we've already put in. So that's all there is to our program. Now, there should be some really obvious assertion places to put some assertions in here. So we include the assertion header, and in our functions, here's a good place for a sanity check. Make sure that since we're just going, we're starting at from and counting down to 0. A really good idea is to check to make sure that from is greater than 0. Otherwise, it's gonna roll all the way back through until the integer wraps around and then come all the way back down again, which is gonna take. And it's 64 bits, so it's gonna take forever. And then in our concatenation function, some really obvious ones. Make sure that our first word is not equal to null. So this is basically it's equivalent to saying if the first word is not null, then we're good. If it is null, if this assertion evaluates to false, it's gonna break at that point, and I'll show you that in just a second. We want to make sure that the buffer's passed in. We want to make sure that the buffer size is greater than 0, and then as a sanity check for our output, you don't need to do this all over the place, but these are actually really helpful, especially as you start adding and modifying code. So what we're going to do is just make sure that the buffer that we end up with the concatenated strings, that the length of it is greater than or equal to. Actually, I guess it should be equal to the first word plus the second word. So when we run this, all we're going to see is the output of the program, and we're done. So this is just printing out what the countdown is, and when we're done, and then when we concatenate foo and bar together here, and we print it out, done, good to go. So all of our assertions passed. Otherwise, if we had done something like concat null to blank and pass in a null and say size 0, which is obviously really broken. When you run that when you're running under the debugger, you're going to get the output will show it. In your console, it's going to show you that an assertion failed. It shows you what the expression was that evaluated to false, and then it shows you which file and line number it's in. Also very helpful. It also highlights the line inside of the editor. So here's where we had our assertion failure. It raises a SIG-abort signal. If that makes sense to you, great. If not, don't worry about it. Just know that we can see that we're stopped at the line where the assertion failed. You can see on the left-hand side is our call stack. So kill was what stopped our program. This assertion return value is also internal. All of these internal functions are all going to be grayed out. Your functions are going to be highlighted with, are going to be colored with the regular black text, and then we can follow the chain of what caused the failure. So we're sitting here at the failure. We can take a step up in the stack and see that that was the line that caused it. So let's get rid of that, and if we've got NSLog, we talked about prior to this in the Objective-C portions of the lecture. One thing that we also mentioned that is really helpful is the %at to get an object, to have an object printout in NSLog. It's equivalent to the toString in Java. It calls the message or the method description on the object. And by default, it's just the class name and the memory address that it's sitting at. That's the default for an NS object. So if you override an NS object or subclass an NS object and you don't provide a description method, you're just going to see class name and address. Otherwise, if you override it, the method is called description, and it returns an NS string that basically gets passed in, and a lot of the, actually, I think pretty much all of the Foundation and Cocoa classes have really descriptive description methods. Like an NS array will print out all of the objects. We'll call description on all of the objects that are contained within it. Windows will show you the frame and bounds, and you'll see a lot more of this later on. So guard malloc, it's under the debugging menu in Xcode 3. That's how you turn it on and turn it off. It's nice to have on, except it adds some time, some startup time to your application, which is why most people don't leave it on all the time. There's some delay. In Xcode 4, you have to put if you're familiar with schemes in Xcode 4, that's great. If not, you don't really have to worry so much about it until you switch to Xcode 4. Xcode 4 is, I'm not going to go into all the differences between Xcode 3 and 4 with schemes, but suffice it to say that when you open up and look at your scheme for this target, when we're running, some of the options, some of the diagnostics for while we're running is to turn on guard malloc. We can turn on edge guards, which are like sentinels that check to see if you do any buffer underflow or overflow writing. And then you can also, this kind of parlays into the being able to check to see if you've got any zombie objects that you've released and that you're sending messages to. So here's an example of what that looks like in action. So let's make a buffer, a character buffer that's a little too small, that's only 10 characters long, and let's concatenate foo with supercalifragilisticexpialidocious, and we're calling it with what we think are good arguments with 2 strings. We're passing in a buffer, and then we're saying, okay, well we'll say that the buffer length is going to be whatever this string length is going to be. So if we don't have these turned on, basically what you'll see come up is you'll just get undefined behavior. So in this case, the application actually ran. I'm not printing. I didn't print it out. You're right. Buffer too small. Run it. So we see that. Did it get it all in there? How did it get it all in there?
The thing you keep in mind, though, is that this is not non-deterministic behavior, so it might work.
It may work or it may not work. What's really nice about having these guard malloc and the zombie objects for Objective-C is that it'll catch most of these errors. The problem is that the only way that it can do this in hardware to make it fast is to line everything on 16-byte boundaries. So if you need really super fine-grained control, I'll talk about that in a second. So in this case, when we run it, it'll generate a hardware error, a bad access error. You can see the function that caused it, because we're trying to do a string copy into a buffer that's too small, so we're overwriting the end of the memory. Also very nice. We drop right into the debugger right at the point of the problem. We can see the stack also on the left-hand side. And then let's see. So Sentinel code is a real common thing. It was a real common thing in the past where you allocate buffers that have extra memory on both ends. You fill it with known values. I like to use dead and beef, DEAD, hex DEAD and BEEF on the ends. Return back the pointer to the memory that you've asked for, and then when you release or you use that memory, you check both ends to make sure that they're still the values that you expect. If they're not, then that means you've scribbled over the ends. You've scribbled too far past the end of a memory buffer, or you scribbled to memory that was not yours, that was allocated before, or that you wrote as a buffer underrun, wrote before the memory that you had allocated. So breakpoints. I tend to, every function that I write, I slap a breakpoint in. It's a good place for a tape stop. So breakpoints are set on the left-hand column here. You just click once on the column to turn the breakpoint, to set a breakpoint. If you click it again, it turns opaque or translucent. That means that the breakpoint still exists, but it won't stop there. It's a handy way to temporarily enable or disable breakpoints without completely getting rid of them. Xcode 4 has also got this nice feature of showing you all the breakpoints on the left-hand side by selecting the breakpoint tab up at the top. So typically what I do is go through and set breakpoints in every single one of my functions that I write, so that when I get to, as I get to every function, I can step through it and watch the states of all of my variables and make sure that I'm getting the correct behavior. So it's slightly different in Xcode 3 because you've got a separate window, but the ideas are basically the same. So on the left-hand side here, you'll see all of your local variables. Actually, if this in Xcode 4, you can set it to just see your local variables, or you can set it to see all of your variables, including the global variables. So right now, set in auto mode. Unless you're using a global variable, it'll only show you your local variables. Here they are. It's one argument, or one argc, program name, and then here's our 256 character buffer that we've created. These are your controls for the debugger. They're large, lickable, candy buttons on Xcode 3 and Xcode 4. Since it's all integrated, they're very small, but the functionality still remains the same, and it's still pretty clear what they do. So the right triangle means just run, just from wherever I'm stopped, just go. The next one over is step over the next instruction. So even if it's a function call, it won't go into it. It's just going to step over it, which I'll demonstrate here. Well, I set a breakpoint. So I'll back up. So step over, we'll just step over each individual line. It won't go into a function. The next two are go into the current function or go into the next function that is called, and this is come out of the current function. Once you start using the debugger quite a bit, you'll find these as really, really handy shortcuts to being able to follow your code and follow your program logic. And then say, like, since I know the countdown is so trivial and it doesn't do anything except for print these numbers out and then say done, I'm just going to say, okay, come out of the function. And I come back out to where I started. The stack is still over on the left-hand side. Now I can go into concat. I can step over each one of these. I can see on the left-hand side all of my variables. These are all of the parameters that have been passed in. If you click on the triangles, these aren't very interesting because it doesn't show you the full contents of what's in the buffer. But you can see that the first word, it starts with F, which was the foo, and the second word starts with B, which is bar. If you right-click or control-click on a value that you have open, you can say, let's show me the memory, and this will show you the memory sitting at that location of what that pointer is pointing to. Xcode 3's got it has it slightly different, but the